Hey, what's up, guys? Yeah, so this is my final topic of my analytic number theory lecture. So this is my number theory video, analytic number theory video if you want to check out. Basically, in this video that I'm gonna to I'm trying to introduce the prime number theorem. But previously, in my previous video that I already described the parallel transformation or the Maling transformation, that kind of formula that you can use. Okay, so in this video, I'm gonna to quickly prove the prime number theorem by using a standard approach. So by using the zeta function approach. Okay, so most of the detail based on the previous few videos about the L function and yeah. So if I say some detail that you don't understand, you can go back to, you can check out my list. I will post the link below. Okay, so quick the recap is that previously we can define this psi of x to be lambda n, and that's equal to x, and this is the Van Moget function, which is defined to be if n is a prime power, that I take log p, else I take 0. Okay. And in the previous video that I also proved that the psi of x is basically if psi of x is xx, the leading order of this guy's x, then one can show that pi of x, which is defined to be the number of prime, which is a sum over p. So the number of prime that's equal to x is the leading order is x plus log x, or x divided by log x. Okay, so this is plus one small one. Okay, so this is the PNT. Okay, prime number theorem. Okay. So in order to do this proof, we need to reconnect this function in terms of zeta function. Okay, so the 201 that is this zeta function that if you sum from n from 1 to infinity, lambda n divided by n to s will be the zeta prime of s divided by zeta s. So zeta s is the zeta function. Okay, now this formula is proved by using the convolution of L function. So if you haven't seen my previous video, that you can go to see this. This is the Dirichlet function, or the Dirichlet series. Okay, now you can prove this by using the formula like this. So basically, you can prove, let's say you can prove the following. Okay, I think you can use this and easy to prove this. Okay, so once we have this is the step 1, we have this, and the next we just using the second. So this is step 1, and step 2 is that we need to do the contour integral, right? Once I do the main transformation. So the idea is that we have the formula, which is the main transformation. That's already this is m of x defined to be lambda n, and that's equal to x, and then by the parallels formula, or so-called Maling transformation, that one can prove this is 1 over 2 pi I. If you want to see a proof, that you should also check my previous video. And this is s x to s divided by s ds. Okay, so in order to do this, we need to close the contour by left-hand side. Okay, so this is c minus infinity, c plus infinity. And in order to do this, we need to understand the 0 and pole of this zeta function. Okay, so this is why we need to do the analytic continuation. Okay, and I'm not gonna tell you this. I think this is the simple fact that I think previously I introduced. Okay, so in order let's quickly do this, right? So we know that the zeta, this zeta function, if I do the analytic continuation, that I will get there's only one simple pole, which is s minus 1, right? So it equals to 1 plus, let's say, something which is analytic, and you can do the derivative, and you get this. Okay, so once you do the contour integral, that what will you get, right? So first you may get let's say s equals 0, so you get the constant term. Okay, so this is the residue. This is the residue which comes from s equals to 0. So this is s equals 0. Okay, and next that you may get the once you do the differentiation, you get s equals to 1. Okay, you get s equals to 1. So you get you get s equals to 1 residue, and the residue is minus 1. So you get 1 over, so it's residue, which is on s equals to 1 of this function, which is 1 times s 1 divided by 1. Okay, plus all the non-trivial zeros. Okay, plus what? All the non-trivial zeros. Okay, so you need to consider a 0 after before this line. Okay, you need to consider 0 less than s less or equal to 1. So let me just continue. So your results will be this. This is just some constant plus x plus the results, right? So, and actually one can count the multiplicities. So basically this you can view, let's say zeta s has a 0, let's say c minus s minus rho. So zeta prime s will be 1. Okay, so you get, once you do differentiation, you get a minus 1 here. So when you take s equals to rho, you just simply plug s equals to rho. Okay, so so you get a minus 1 summation of rho, which is all 0 of zeta function less or equal to 1. So x divided by rho. Okay, and lemma that I will show in the next video is that this zeta s is non-zero for real s equals to 1. So zeta function has no 0 on the s equal to 1 line. Okay, so you can modify this term in terms of, let's say, constant term plus x plus minus 1 rho, real rho less than 1, and all zeros. So zeta rho equals to 0. Okay, and these two terms can be deleted, can be classification in terms of two terms. The first term is the Riemann hypothesis, all the s equal to half part. So all the s equals to half part, this is called non-trivial zeros. And for s less than 0 part, this is called the trivial zeros. Okay. So finally, let's consider this plus x minus the non-trivial 0. So this is a non-trivial 0, where zeta rho equals 0. So x rho divided by rho minus the trivial 0. Okay, and the trivial 0 is s equals to minus 2n and greater or equal to 1. Okay, so it's on the -2, -4, -6. Okay, so for this one, you get 2nx plus. Okay, and then minus 2n. Okay, now you can easily use your Taylor expansion to prove that this is just log 1 minus 1 over x squared. Okay. This is not difficult. Sorry, this is, yeah. Okay, this is not difficult, and okay, but no matter what, which I proved that so you basically prove that this psi of x is basically the leading order term is x, and the rest of it's the rest of real rho is at least less than 1. So you prove the zeta function. You prove the prime number theorem. Okay, so this is the proof. The proof idea is just this. And I think the detail that I already explained in the previous few videos. Okay. And but there is some technical issue. So let me explain. So one technical issue is that one actually can show this guy is basically well diverged. So actually this formula is not okay because actually the left hand side is converged, absolute converged, right? But right hand side is probably not because due to these terms. Okay, so remember that so let me just write down the modification. So this is like the actually the real the 100% rigorous formula. If you can prove that this, so one can show that all the non-trivial zeros, 1 over rho square is less than infinity. Okay, then you can use our second main transformation. So one can define psi1 of x to be summation of lambda n minus x. Okay, and that's equal to x. And the second main transformation is proved by my previous video. Is this 1 divided by 2 pi I and minus theta s prime of s theta s s plus 1 s plus 1 ds. Okay, so obviously that this psi1 of x is basically 0 to x psi of y dy. Okay, so if psi of y is approximate y, the leading order is y, then psi1 of x should be leading order have x squared divided by 2. Okay, so I can use the same techniques to prove the zeta function, right? I can to prove the order of this psi1. Okay, so I do exactly the same thing. So I take s equals 0. I get a least term. Okay, x, because s equals 0, then I plug 0 plus 1, x 0 plus 1. Okay, and for s, so this is s equals to 0 pole. And this is s equals to 1 pole, right? So I get x squared divided by 2. Okay. Actually, this sorry, this is I should say what? I should say this is original s equals, sorry, the original s equals to 1, 0 of zeta function. Okay, because I just plot s equals to 1, I get 1 times 2, which is x squared. And also s equals to minus 1 term, right? So I get this. Okay, and I get constant term, which is not important. And then minus all the rho, which is x rho plus 1, rho plus 1. Okay, and by the previous results, that rho less than 1, which rho plus 1 less than 2. Okay, then you prove the prime number theorem. But this formula is actually rigorous because 1 over rho square is absolute convergence. So this is this formula is the complete description of the establish the complete description of the prime number theorem and basically the distribution of primes and the Riemann zeta function. Okay. And I think this is enough. If you want to know more details about prime number theorem, then I will leave the reference below if you want to know the actual like aerial terms. So you need to go to some detail and do the analysis of this contour integral and try to bound each arc, which is very technical. Okay, but this is the quick idea of how you can use the previous maybe 10 or 20 analytic numbers theory techniques to prove these kind of things. Okay, and I will skip the zeta function. In the next video, I will quickly recap the zeta function analytic continuation and also prove the lemma 1. So I think this is all you need to know. Okay, so thanks you guys. See you.